So with Lewis structures, it really gave us an idea of how the atoms are connected in the molecule, but it does not tell us the actual shape of the molecule. So that's the last part of this chapter. It's not my favorite to teach, and especially on video like this, because I can't show you the structures in person. But I do have a handout for you in Canvas, so make sure to print that out. It's really helpful. It has all the geometries on there, everything you need to know. So that handout's very helpful. Okay, so the way we figure out the geometry of the molecule is we look at what's around the central atom. So we're going to look at, do we have bonding electrons, or do we have lone pairs around the central atom? That's going to determine the shape of the molecule. So for our geometry, we use the VSEPR theory, which is the valence shell electron pair repulsion theory. So all that means is these electrons in the molecule are negative, and they are going to repel each other to get the best possible arrangement. And again, it all depends on what's around that central atom. Okay, the domains, electron domains, are just, can be a single bond, a double bond, a triple bond, a lone pair, and all of them count for one domain. So here on this molecule, the A has a lone pair, so that would be one domain. It has a single bond, that's one domain. A double bond only counts as one domain, so does a triple bond. So total, we have 4 domains around A. So we're going to be looking at 2 different types of geometries. Electron pair geometries, that's just a very general geometry. That's based solely on the number of domains around the central atom. And then molecular geometries, we're going to break it down into how many bonding pairs, how many non-bonding pairs do we have around the central atom. So first we're going to start with the electron pair geometries. So I just have them in a table here. So if I have 2 domains around my central atom, then the electron pair geometry is linear. If I have 3 domains, then it's trigonal planar. If I have 4 domains, it's tetrahedral. 5 domains, trigonal bipyramidal, and 6 domains, it's octahedral. So it doesn't matter what it is, we're just looking at number of domains for electron pair geometry. So it also has the bond angles on there, so you do need to know those, because some of the names we're going to look at for especially trigonal planar and tetrahedral, they have the same name, but we know the bond angle is what makes them different. So be sure to have those. And again, that's all on that handout. The bond angles, the electron pair geometries. But on your handout, the electron pair geometries are labeled as orbital geometry. That's the exact same thing. Okay, so now we're going to get into the molecular geometry. So first is linear. And you'll find that if we only have bonding domains, it's the exact same name as its electron pair geometry. So linear here has 2 bonding domains, 0 non-bonding, and it's linear. So be careful, because just because you draw a Lewis dot structure linear does not mean it's linear. So let me give you a quick example there. So water. I drew this molecule linear in the Lewis dot structure, but it's not linear. So linear shape only has 2 bonding domains, and that's it. But here, water has a total of 4 domains. It has 2 bonding, let me just circle these, 2 bonding, and then it has 2 non-bonding domains around it. So 4 domains, so this would not be linear. So CO2 here is the example for the linear. Again, double bonds only count as 1 domain, so I have 2 bonding domains. Okay, then we have trigonal planar. There are 2 molecular geometries in trigonal planar. The first one is trigonal planar, so remember, if I have only bonding domains, it's going to have the same name as the electron pair geometry. So trigonal planar, we have 3 bonding domains, 0 non-bonding. So BCl3 is an example of that. Okay. And there's 120 degrees between the outside atoms. And then here's the bent shape. That was our next one. This one has 2 bonding, 1 lone pair, and it's called bent. Okay, so that's it for trigonal planar. And then next is tetrahedral. Tetrahedral has 4 bonding domains and 0 non-bonding domains. And then we have trigonal pyramidal, has 3 bonding, 1 non-bonding, and then bent, here's that name again, bent has 2 bonding and 2 non-bonding. So let's look at the structures for these. Okay, so let me give you some examples. Okay, we have CH4. Whoops, don't want to use that one. CH4 would be an example of tetrahedral. We have 4 bonding domains and 0 non-bonding. Okay, so the bond angle between the hydrogen atoms is 109.5 degrees. And then we have NH3. Okay, would be an example of our trigonal pyramidal. So we have 3 bonding, 1 lone pair. Okay, and here, so I told you tetrahedral had a bond angle of 109.5, but the lone pair actually causes these bonds to shift down, and so we get 107.5 for the bond angle between the hydrogen atoms in this one. So this lone pair is really big, and it makes the bond angle between the hydrogens lower. And then for bent, we have water. Oops. So water, we have 2 bonding, 2 non-bonding. So water actually looks like this. And the bond angle between the 2 hydrogens in this one is 104.5. So I'm not going to ask the specific bond angles. I'm just going to stick with 109.5. But I wanted to show you that these lone pairs are big. They're bigger than the bonding pairs, and they push those bonds closer together. So the more electron pairs or lone pairs I have on the central atom, the closer those outside atoms are going to be together.